Welcome to wave-particle duality. We're going to start off by talking about diffraction. Diffraction is what happens when a wave passes either through a gap or near a boundary. We're going to study what happens when it travels through a gap. So we have a diagram here that shows the peaks of a wave. So here is a wave, and this line here is one peak, and the next line is the next peak. And you'll notice that the distance between peaks, that is the wavelength of the wave. The gap that the wave is passing through is many times larger than this wavelength. So the distance of the gap is many, many times larger than the wavelength. In the second diagram, the gap is still several times larger than the wavelength, but you can see diffraction starting to occur. We have this peak here, and it passes through the slit, but on the edges it is starting to bend. You can see there. And that bend continues and goes on. The wave is starting to spread out. It is spreading out beyond the size of the gap. So the size of the gap is still larger than the wavelength, and we are getting some curvature. The final one, this is maximum diffraction. And you can see here that these peaks are almost part of a circle. So if you imagine that you have a circle, we're looking at this section here. Okay, so this is maximum diffraction. And you get maximum diffraction when the gap is the same size as the wavelength. So if the gap stays the same, but you are changing the wave that's passing through, you're going to get different types of diffraction. Or if you have a wave and you change the size of the gap, you can change the amount of diffraction that is occurring. So the type of diffraction that you get is dependent upon the gap that you're passing through and the wavelength of the wave that's doing the diffracting. Please note that diffraction is a property of wave behaviour. Only waves can diffract. A particle that's approaching this gap would either pass through or not pass through. A particle would either hit the wall or it would pass through the gap. So we would not see this spreading out if we were dealing with particles. Let's have a look at properties of waves and particles. So this diagram here on the left, what we can see is we can see two dippers. So these are needle-like structures connected to an oscillator, and what they do is they go up and down and they touch the surface of a liquid. So if we were to view this side on, we would see the surface of the liquid, and this dipper oscillates up and down and it touches the surface and creates waves that spread out from this center point here. And these dippers are making waves centered around their points. See, the wave fronts are spreading out from this dipper over here and also from this dipper over here. And you can see that the wave fronts are overlapping. And where they overlap, they interfere with each other. They either add together and reinforce each other. So for example, over here you have peaks with a larger amplitude. And then in some locations, like this one over here, you have areas where the waves actually cancel each other out and you end up with no peaks at all. This is called an interference pattern, and we're going to be studying it much more closely later on in the course. But for now, all you need to know is that waves, when you have two sources of waves, the wave fronts overlap and they create an interference pattern. This is a behaviour of waves. Here we have a piece of equipment called an electron diffraction tube. And what we have at the back of the tube over here is we have an electron gun. It consists of a cathode, which emits electrons, an anode, which accelerates the electrons, and the electrons travel from the back in a straight line to the screen at the other end. And they light it up. And you can see that in the middle we have this cross structure. This is a Maltese cross. It's a very distinctive shape. And we have a shadow of that cross being projected onto the screen at the back. And this demonstrates to us that electrons, when they are fired, they travel in a straight line. If they hit the cross, then they cast a shadow. And if they miss the cross, then they come through and they hit the screen. Now, some students don't believe that we're actually firing electrons, and one of the ways that we can prove that these are negatively charged particles, because remember, an electron has a negative charge, one of the ways that we can demonstrate this is to put a plate above the tube, and we can either charge it with a positive charge or we can charge it with a negative charge. And what happens is that the electrons are attracted towards that plate and the shadow is deflected. So the shadow actually moves up. So instead of having the cross in this position, the cross would be slightly above. So we can deflect the path of the electrons using a charged plate. And we can do something very similar using a magnet as well. In fact, this piece of equipment here is very similar to what you used to get in the back of a television set. So an old cathode ray tube television, the ones with the very long backs to them, they used to have an electron gun in the back, and the path of the electrons was controlled using fields. And we could change where the electrons were going so that they hit the screen at different points and lit up the different parts of the screen in different colours. And that's how TVs used to work. Now, if we take this piece of equipment, we take away the Maltese cross and instead place a very thin piece of graphite in its path, we get a very different pattern again. So here is what that thin piece of graphite would look like. This is the structure of graphite. It occurs in very, very thin sheets with a very regular crystalline structure. So this is graphite. And if we place a thin piece of graphite in between the electron gun and the screen, then what we get is this pattern over here. We get a central dot, and then we get rings of light. And in between, we have dark patches. So here is a dark patch between the rings. Here is another dark patch between the rings, and so on. And this is actually a diffraction pattern. So we are getting diffraction as the electrons pass through these small gaps in the graphite. As the electrons pass through these small gaps, they diffract through the gap. They are diffracting through many, many gaps. And as they pass through the gaps and they spread out, just like the waves here, they overlap and they interfere with each other. This diffraction pattern is an interference pattern as the electrons, behaving like waves, overlap and cancel each other out in some parts and reinforce each other in others. Which is unusual because an electron is a particle. An electron is not a wave, or is it? So we know that waves exhibit diffraction, and yet here we can see that electrons are showing that same behaviour. And it turns out that all particles exhibit wave-like behaviour under specific circumstances. And this is one of those circumstances. These are some photographs of the famous physicist Louis de Broglie. He developed an equation that helped us to understand the behaviour of particles and when they exhibit wave-like behaviour. He helped us to understand that all particles with mass and a velocity have their own wavelength. So if we take an electron, for example, and the mass of an electron is 9.11 times 10 to the minus 31 kilograms. If we fire that electron at a high speed, let's say it's moving at 100 meters per second, then we can calculate the wavelength that that electron will exhibit. So we've got Planck's constant at the top here. So an electron moving at this velocity will have a wavelength of 7.3 micrometers. But the electron is a particle. If you were to pass the electron through a gap that is the same size as its de Broglie wavelength, then the electron would exhibit diffraction. So in this situation here, if this gap was equal to the wavelength, then you would get the electron behaving like a wave. If the electron was moving faster or slower, then you would need a different size gap to get it to exhibit that behaviour. So you'll notice that the mass times by the velocity is the momentum. And we often talk about changing the momentum of a particle, which would usually mean changing its velocity, given that the mass of a single particle is fixed. If we were to change the momentum, then that would lead to a change in the de Broglie wavelength of that particle. So for example, if the velocity was larger, then the wavelength would be smaller. If the velocity was smaller, the wavelength would be larger. So instead of having this distance here between the peaks, if the wavelength was larger, then we would have a larger distance between the peaks. A larger wavelength means that you need a smaller gap in order to get diffraction. So we would actually get some diffraction at this level. And this one over here, the gap is much closer to being the size of the wavelength. So we would get more diffraction. In this situation here, the gap is actually smaller than the wavelength. So the wave would be blocked, it wouldn't be able to pass through. If you had a smaller wavelength, where the peaks are very, very, very close together, then you would get no diffraction happening here. The gap is just far too big. The wave doesn't really notice that there's a gap at all. Same thing would happen in this situation. You would get very, very, very little diffraction when the peaks are so close together. and then you would start to see some diffraction happening in this situation, but not very much. So depending upon the relationship between the size of the gap and the wavelength, you're going to get different types of behaviours. And for individual particles where the mass is fixed, it's the velocity that changes to change the momentum, to change the de Broglie wavelength. So in summary, the de Broglie wavelength is the wavelength that describes the behaviour of a particle and when it exhibits wave-like behaviour. You can calculate your own de Broglie wavelength yourself. So we can do that now. So let's take a runner. A runner is a particle. A person who is running is a particle. And we can calculate their mass. Let's take the mass of a typical human, so approximately 80 kilograms. And a person can run at, if we look at the world record, that's approximately 10 meters per second. And we can calculate those values. So 6.63 times 10 to the minus 34 over those values will give us a very, very small number indeed. So for human beings, running at a high speed, that person, that runner, would start to show wave-like properties, and they would diffract if they were to pass through a gap that size, which of course is impossible for the human body. So objects like people do not exhibit wave-like behaviour, but small particles like electrons do. And the de Broglie wavelength helps us to understand whether a particle is going to exhibit wave-like behaviour. Louis de Broglie won the Nobel Prize in 1929 for his ideas. But this was just the conclusion to a long period of study and research into the nature of matter and light. Isaac Newton in the 17th century proposed that light was made of particles. Huygens proposed that light was made of waves. Thomas Young found that light exhibited wave-like behaviour. And Einstein observed that light had particle-like behaviour. There were lots of scientists that contributed to this work. And it was Louis de Broglie's discovery of this equation and his observation that electrons, which are definitely particles, have wave-like properties that brought everything together. But it was a collaboration between scientists that led to this discovery. New knowledge is built upon old knowledge. New discoveries are built upon previous understanding. Theories are tested to see if they work, and if they are found not to work, new theories are developed. There needs to be peer review, colleagues working together and checking each other's work in order for new scientific theories to be validated by the scientific community.